Okay, so as it was mentioned, so we're going to record it, so it's going to be available then for everybody to download at. So welcome everyone to this webinar on the geotechnical site investigation for building foundations in permafrost zones. And it is in essence a summary of the standard BNQ 501500, which became available in 2017. Now, just to remind everybody again, please mute yourself if you can. I know people are joining later, and we're trying to mute everybody, but so that we don't have a lot of background noise. That would be very much appreciated. And also, if you could turn off your cameras, that can help with bandwidth for those that are located in areas with very limited bandwidth. So thank you very much, and I appreciate that. Also, if you do have comments, please use the chat window or questions and write down your question there. You can either address it to everyone, or you can address it to the presenter, myself, or Elodie, and then we can respond either right now during the webinar, or maybe if it's more complex, we'll follow up later with an email. So this standard was part of a larger initiative, and the initiative initiated by Standards Council of Canada was the Northern Infrastructure Standardization Initiative, or NISI for short. And it's the aim to develop standardized strategy to address the unique climate, geographic, socioeconomic, and cultural circumstances for Canada's North. It was recognized that the North is different than southern areas, and that really was the driver behind these standards. There are currently about 10 standards available and 2 guidance documents. They can all be found on the SSC website. Now, many of these standards are actually now also in revision, or just new standards have recently been published again, a newer version of those standards. I do want to start also with a disclaimer. The text is pretty much copied right away from the BNQ 25010-500 standard, and it mentioned that yes, it is a standard, but it is a reference document for voluntary use. So it's up to the owner or the engineers whether or not you do want to use this document. But probably if you do not want to follow the document, you must find good reasons why not to do it. But it does provide a certain guidance of where to go. Now, before diving into the actual standard, I also like to acknowledge that it's not just a one-person work. There are actually a large group of people that supported the development of this guidance. So there was, first of all, the Standards Development Committee. I'm not going to read all these names, but it's a large group under the chair of Sarah Brown. She was chairing this committee. And then there was the working group, which I had the pleasure to and lead, as well as additional collaborators. All of these people helped developing this standard and made it possible that we do have this standard. Now, the content of my presentation is in essence following the actual standard. So you will see the same headers and the same the same structure in the standard as you will see during my presentation. I will also have reference to specific sections of the standards will show up in the presentation. So we'll first start with the scope, we'll have a couple of definitions, then we'll go into how to plan the site investigation, we'll talk about the qualifications needed, and then the 2 levels that we propose for site investigation, which is a preliminary site evaluation and then the actual site investigation. And last but not least, the reporting and recommendation, which is an essential part of any geotechnical site investigation. Now, what is so special about the North or working in permafrost environments? The key here is that the permafrost, so the frozen conditions, make it challenging because we now have ground ice, and those that have worked in permafrost and in the North know that ground ice comes in various forms, different shapes, different colors, if you wish, and different temperatures. And the strength and the response of your foundation really depends on the response of the ground ice. We also have saline soils. So in particular, when you get close to the Arctic oceans, there are areas that have salinity. And when we have salinity, that affects the freezing point. So in other words, how much of your ground is still frozen. So you may have unfrozen condition at temperatures that are still below 0 degree. So if we purely go by definition, then we would have permafrost, but it's unfrozen. So from a geotechnical perspective, this material acts like unfrozen material, but from a thermal perspective, it is actually permafrost. And on top of that, there is climate change. And when you look at how climate change currently affects our globe, the Arctic is affected much more significantly than the rest of the globe, or if we take an average. So we have increased warming, but not only the increase in air temperature affects our foundation, but also related changes such as changes in precipitation. So how much water do you now have? So that affects your surface water and affects advective heat transfer, for example. Or when you look at communities close to the coast, there we have longer open water season. So we are affected by increased impact from wave action, or also changes in weather patterns, being in precipitation, snow, and so on. So there's a multiple function that climate change will have on our foundations. Now, it's important to recognize that the level of detail of a geotechnical site investigation really depends on multiple factors. And that was one of the reasons why, when we did develop this guidance, we didn't want to be too specific and too descriptive. So the idea is really to give the professional the tools to work and use their experience, and also address the specific boundary conditions that we have in the Arctic. So it's really, this guide was developed to provide the information that will allow for the design and the maintenance of building with a reasonable time frame and cost. And we completely acknowledge that every case is similar, is different, it's not similar. So having just a one-fit-all solution does not work on all these different challenges that we see in the Arctic. And therefore, the focus of this document, when you provide a consistent methodology. So the approach should be similar, so that geotechnical engineers, but also owners, understand what is to be expected and what needs to be done. We'll also focus on a dialogue between the designer and the owners, so that everybody understands where to go. And the key is to have these distinctive characteristics of permafrost addressed in your design. And that includes also the seasonal and interannual climate conditions, as well as where is the climate going to be towards the end of the service life of your building foundation. And there's also other considerations that may have an impact on your building foundation. So that leads us to the main scope of this evaluation, of this standard. It is to provide the essential information so that a building foundation can be properly designed, or if you need to do some rehabilitation for existing building. And both aspects are probably going to be significantly important in the future. So the principles laid out in the standards are specific to geotechnical site investigations, and it's really applied for buildings. So that's how we designed and formed this code. However, it may also be applicable to other types of infrastructure. And we understand there are currently not standards, for example, for road embankments, or if you're working more in the mining sectors, being it for dams, or if you have a sewage dam that you need to build. So the focus is really on buildings, but it doesn't mean that the general guidance cannot be applied to other types of infrastructure in the north. And it is primarily aimed to geotechnical consultants, but it also is for the owners of the buildings, designers of buildings, contractors, and regulators. So it's to give everybody an understanding and a common language to talk when we do building foundations in the north. Now, before we dive into, it's important that we all talk about the same issues. And therefore, we have a section on definitions. And I'll just pick two definitions right now, or two slides on definitions. The first one is, what is permafrost? And to me, the trumpet curve is always the most important graph when it comes to permafrost, because I think if you understand the trumpet curve and this particular graph, you actually know your permafrost. So there is a lot in this graph, and that's why it's so important to actually understand this graph. So first of all, you can see the definition of permafrost. So we do have the permafrost table with the active layer, which is the layer that freezes and thaws during the seasons. Then we're at the top of the permafrost. And then as we go deeper, we reach the base of the permafrost. This is where the ground temperature again gets into a positive range. Now, on the left side, this, for engineering purposes, it's probably more important to understand the left side than even the right side. Because if you go back to the definition of permafrost, which is purely time and temperature dependent, on the left side, we talk about what is frozen. And as I discussed earlier, salinity can result in a freezing point depression. So the actual layer that freezes and thaws, so from a physical perspective, where you have a change in the phase, can be deeper than the permafrost table. And as well at the base, you could have a layer where the ground is unfrozen, so behaves like unfrozen soil, but is still in permafrost, where we talk about a basal cryopack. And these aspects are important, for example, when you build your pile foundation. So you need to know what are the conditions, the thermal conditions of your permafrost if you want to use it as your resistance. And the other parameter where I quickly want to define is what is a geotechnical consultant. So we provided that definition because the geotechnical consultant is ultimately responsible for carrying out the geotechnical site investigation for the client. And in French, just it's the expert conseil en géotechnique, just to be aware that this is a term that comes with responsibility. So you as a geotechnical consultant have the responsibility to carrying out and be responsible for the geotechnical site investigation for the client. You're representing the client, you're providing the client with that guidance. Now, so let's dive a little bit into the workflow how we formulated this standard. Now, I understand this is a busy slide, and I'll go to the aspects that you see here on the left, but in essence, this graph on the left-hand side, which is a little bit simplified here on the right, shows you how we envisioned and propose how to do site investigations. So first of all, you do have a project, you go into the initial planning, you bring in your client, you bring in your geotechnical consultant, and then you do your preliminary site evaluation. And you see here the section 7 or 8 or 9 or 5, this is in reference to the actual guideline. At the end of your preliminary site evaluation, there will be a report. And the key with any report is that you provide recommendations. And at this point, recommend whether the site is okay and you have enough information, you can go into a foundation design. Or you think this site is okay, but you're not sure, or you do not have enough information for proper design, so you go now into your site investigation. And then there's also number 3, which tells you that you do have sufficient information for both cases, and you can either go with an alternate foundation. So for example, you were considering shallow foundation, but you need a deep foundation, so that is a significantly change in your design, but you do have sufficient information. So you propose the alternate foundation, then you can go into foundation design, or you do have sufficient information and think, well, this site is not suitable. And then I guess it's back to square one to reconsider what needs to be done. Now, if you end up with number 2, you do your additional site investigation. So now you're collecting additional information, and the outcome of this site investigation, again, will be a report with the same sorts of potential recommendations. So either you can come up with a foundation design, you have enough information to design an alternate foundation, or at this point now you have to evaluate, well, this is not a suitable design. So this is just the general workflow that it is recommended. And if we go a little bit closer, then you see these streams called A, B, C, and D. And what they refer to is different type of additional investigation depending on your project risk. So you do, again, we're here in our preliminary evaluation, which is focusing on desk studies. We'll go into that, which then helps you to do a climate change risk evaluation. And based on your risk related to climate change, in this particular case, there are 4 options, and we follow CSA plus 4011, where we say either the project has a negligible risk, it has a low risk, it has a moderate risk, or it has a high risk. And depending on this risk, you would then have to choose a different set of investigations. And without going into too many details here of this flowchart, you can imagine that for a low risk conditions, you probably don't need as many investigations as for a high risk foundation. So if you have a high risk foundation, being it because either your structure is very sensitive to deformation, or you have a very susceptible foundation, ice-rich conditions, warm conditions, then you need much more detailed assessment. And the guide provides you with these different levels of investigations that are required depending on the actual risk assigned. Now, when we plan, the levels that we need or the aspects that we need are A, we need to know our surface conditions. So we need to know what's the building site look like? What is the topography? Is it slope? Is it steep? Is it flat? Do we have vegetation? What is the superficial geology? what is the drainage, for example. So they're all aspects just related to the surface conditions. Next, we need to understand what is the subsurface. So what ice do we have? Where is the bedrock? So if we have shallow bedrock and we excavate, for example, if we have deep bedrock, what are the conditions? What is the characteristics of the ground ice? What is your ground thermal regime? Because these really dictates what type of foundation you need. But also, what is the borrow material? Do I have a good gravel source or do I not have a gravel source? So these, let's call them more external components, are critical in your design of your foundation because they may drive the economics. If you do not have a gravel source, then suggesting a gravel pad is simply not an option, even if it's technically the best option. And then the third element is the climate condition. And here we talk about seasonality, but also interannual climate condition. So multi-year variations. So we have larger scale climate driven conditions. And then finally, the projected climate change. So what is the climate conditions during your service life of your building foundation? And the last of these four larger bullet points is the risks, for example, arising through to seismic hazards or anticipated changes in the building. So very often in Arctic areas, we actually have one foundation, but the building may change because the foundation is quite expensive and it's possible that we're changing what type of building or what's the use of this building. So we need to anticipate if there are changes to your building in the future, which extends the service life of the actual building foundation. So when we then start working with the client on this, it is important to have that common understanding. So we need to know what is the building description. So obviously, where is the building? What is the configuration? What is the size? Above ground? Do I need to have a flat entrance? And so on. So these are important consideration and should be made available to the geotechnical consultant right at the beginning. So yeah, what's the purpose of this building? What are the operating conditions? So how will you use this building in the future? And then we're going to see the loads. So what type of loads do we have? What's the service life, building foundation? And again, recognizing that the building may be retrofitted several times over the original foundation. So that's not uncommon to do. What tolerances are accepted? And also, where do you have utilities or any other structures? And also, are there any schedule limitations? Access to, being it workforce, being it equipment, can be very limited in remote areas. And as such, the construction schedule can be the actual design criteria and the driver for why you use a certain design. So that's, again, different from what's happening typically in the South. And what the guidelines and what we really want to focus on is this common understanding. So it should not be that one party is ordering something and let the geotechnical consultant do the rest, and then he or she will come up with the fixed solution and everything ready. It must be a dialogue, and it must be a common understanding that actually changes throughout the project. This is very important for a successful foundation design. We also talked about the qualifications, and we had some lengthy discussions, and this is the text that is now in the guide regarding to what qualifications or what qualifies you to work in these environments. And again, we wanted to be very prescriptive and not just checking boxes in terms of what courses did you take or what standards you apply to. So first of all, yes, as a geotechnical consultant, you must be licensed to practice in your territory or province. So that's not new. But it's also important that anyone working on this project shows the training, experience, and expertise that is relevant to the subject matter. So you must have experience working in these areas, in this training. That includes any subcontractor, any subsurface investigation crew, so being it the drillers, being it geotechnical people. So you must demonstrate that you have the proper equipment that is capable of working in these environments, and also that you got the training and the expertise. Doing geophysical investigations in an Arctic environment is different than if you do it somewhere in a southern, more warmer condition. The same goes with drilling. If you do sampling, geotechnical drilling with sampling is one thing, but even storing and handling your samples once they're out of the ground is a very complex and important part of the site investigation. And it requires that the people involved do have that expertise. And it all works under the direction of the geotechnical consultant. So ultimately, the geotechnical consultant is responsible for doing this. But we wanted to write it in this way so that everybody, being it owner, being it subcontractor, being it the geotechnical engineer, including regulators, are aware that it's key to bring in that experience. If people do not have the experience, it's better not to use them on a certain job. Now, let's dive a little bit into those two steps that I initially described. So first, we do have the preliminary site evaluation and then the site investigation. So the key scope, I would say, of the preliminary site evaluation is to assemble available information. So there isn't any site where there's no information. Typically, when it comes to building foundations, so you're either already at a hamlet or a smaller community, so there's probably some sort of information available out there. So that's why we're trying to do, in a first evaluation stage, bring in the necessary information. So that includes really mainly desktop evaluation. And then if it considered necessary, you can have an additional site visit. And then you do what I've explained earlier, that initial site risk level evaluation, which gives you then a guidance on where to go next if you need to go into a detailed site investigation, or simply also what level of information do you need? Do I have enough information? Again, as an example, if during the site evaluation you see that you are at a level D, so there's no risk to your foundation due to climate change, then the information that you have at this point may be sufficient to go into your geotechnical design. But if you have a high risk rating, then you may not have sufficient information to provide the foundation design at this point, and that triggers then the next level of site investigation. And what do we need? So for desktop evaluation, and these are typically just all sorts of aspects that we've been listing, but you as a geotechnical consultant need to decide which aspects are actually important. So when the guides or the standard does not say you need to address every point, but it just provides a guidance, as I mentioned at the beginning, what should be addressed. So for example, we need initial assessment, we need seismicity, surface geology, geomorphology, groundwater, vegetation, and so on, permafrost characteristics. So those are all the points that are listed that either you don't want to use it as a checklist, but it gives you guidance on what to do. And when deemed appropriate by the geotechnical consultant, a site visit should be considered. And the key at this point is really just to validate the information that you have been collecting during that initial evaluation stage. Some of the information may be outdated, so it's important to go out there and have a look. But again, it is at the discussion between the client and the geotechnical consultant to show whether a site visit is important. Why did we hesitate and make it prescriptive at this point? It is also because of schedule. So we're dealing again with remote communities at times, and therefore it may not be practical, or it may delay the foundation design and the construction significantly. But it's up to everybody to consider what are the associated risks with a certain decision. Now, the level of risk that I introduced earlier, the D, C, E, and A, really comes out of this CSA plus 4011 document. So I refer to this document. It's also available. It's one of the NICE standards. It's also available for free and has very recently been renewed. So there's a 2019 version, and it also has a technical guide that provides additional detail on the design and construction consideration for foundations in permafrost region. So there's a complementary document, I would say, to this BNQ standard. And while I understand that it's probably hard to read the figure at the bottom left, but what it does in essence is we're evaluating what is the sensitivity of your foundation to climate change and what are the consequences. So again, if you have a high sensitivity foundation with a high consequence, then that's when you end up in the A. If you have a low sensitivity to climate change and you have a low consequence, then you end up in the D. So it's not very sophisticated or complex, but it's just a level of evaluation, a simplified evaluation that should be done. Now, at the end of your preliminary site evaluation, which is section 7.5, you will come up with 4 options. So either you do have sufficient information to go into a design, or you do not have sufficient information to go into a design. Sorry, there's some background noise. So yeah. If people could mute, that'd be appreciated. I've been trying to mute all, but it's working. So again, so you have option 1, you have sufficient information to proceed. Option 2, you do not have sufficient information to proceed, or you go and have sufficient information to make alternative recommendation, or you have sufficient information to say, well, this site is not suitable. Now, if we go into section 2, option 2, which is likely the most cases, then we go into a detailed site investigation. And that really depends on different conditions. So what is your risk to your foundation? And here we're providing a set of methodologies that could be used to do this. So you want to have more details on your climate change projection, for example. So you want to reach out to climatologists or to other sources to help with understanding what are your environmental conditions in the future. You want to use other technologies. You want to use remote sensing, for example, INSAR. You want to use geophysics, and important, obviously, what is your soil conditions? What is your ground ice? What is your thermal conditions? Get samples out of the ground. So the standard then provides all sorts of different methodology, and it also provides tables. So this is table D1 in an appendix, where in this particular case, we're summarizing all sorts of different geophysical methods that can be used, and we're talking about some pros and cons and commentary for those different methodologies. But understanding that it may not be applicable and may not be available at all sites. We also provide guidance on test pits and drilling. So for example, at this point, a minimum of 3 boreholes should be drilled at a test site just to understand the heterogeneity. And we also provide as a guidance, as a reference, that a minimum of 1 borehole for every 200 square meter. And also they should go at least 10 meters, preferably 15, but for sure, greater than the anticipated pile length. And so there's two aspects to this depth, for example. So one is to really understand the ground thermal regime. So where's the depth of zero annual amplitude? How does your permafrost temperatures look like? And then the other part is, if you have piles, what is the at-freeze resistance? Because if you have a pile that freezes into your surrounding, you definitely want to know how the strength develops. We also provide recommendations in terms of sampling intervals and if those samples need to be taken. Now, drilling, there are books about drillings, so we do not want to go into all the details. And more often than less, it's really what equipment is available on site that dictates what drilling you're actually going to use. Nevertheless, we provided a couple of tables in the Appendix C that show pros and cons for different drilling methods and sampling methods. So from rotary drill to diamond drill or sonic drill and other lightweight or heavy drill. So there's a whole table that gives you a little bit of understanding. And then when you have these samples, we also make recommendations in what you should actually evaluate. And in addition to the standard classification between ice, no ice, bonded, well bonded, we also recommend that we use the crystography that has been based on Merton and French, as well as Lynn and Kaplar. Their talk about what type of ground ice do we have? And I'll soon show that in the next slide. We also simplified the volumetric ice content in terms of 5 classes. So either you have pure ice, which is in essence 100%, and then we introduced this term called soil poor ice, soil rich ice rich soil, and ice poor soil. So these categories, these 5 categories, provide an initial assessment of the range of ground ice content. And we base this on potential settlement. So if you have ice poor soil, you actually do not expect a lot of thaw excess ice and as such a lot of thaw strains. But as soon as you get into ice rich soils, the thaw strains can be quite significant. And I was mentioning Merton and French. So this is their guidance where they look not just at how much ice do you have, but what is the stratigraphy and the cryostratigraphy in particular. So do I have structureless ice? Do I have lenticular ice? Do I have irregular reticulate ice, regular crustal suspended? So if you make those descriptions, they help later to analyze where did the ice come from. And that for a designer can be an important information when it comes to the strength that this material develops or not. Again, here we do have layered or lenticular ice, parallel, non-parallel. So these additional information are strongly recommended when you do your logging of your ice cores. Now, understanding your ice is one thing, but understanding your temperatures is the other aspect. Because if you have cold permafrost, then your sensitivity to climate change is much lower compared to warm permafrost that is already sitting at 0 degrees. So if you're already at minus 0.1 or actually sitting at 0 degrees, then a 1 degree warming has different consequences than if you are sitting at -4 or -5 degrees with a permafrost. And that's why it's so important to use ground temperatures to understand your changes over time, to understand what is the minimum, what is the maximum ground temperature, what is your mean annual ground temperature, so for example, at the depth of 0 annual amplitude, but also what is your active layer thickness. So once you have your active layer thickness, that is also an important design parameter for piles, for example, or also shallow foundation if you want to replace your material. So having a good understanding is important. And we do provide, again, some recommendations on what instruments should be used, and we're not in terms of a brand, but a thermistor string is definitely recommended, and data logger is very strongly recommended at these days. Now, one also needs to keep in mind that when you drill, you generate thermal disturbance, so it's not sufficient to drill, lower thermistor string, and then measure the temperatures right away, because those temperatures are most likely affected by recent drilling, and therefore having a monitoring logger or a data logger installed to it and to see how the temperature change, and once they're stabilized, that gives you a good understanding of your ground thermal regime. In terms of what you look at it for the soils, we have a list of recommendations, some simple index properties that we should look at, like any types of geotechnical investigation. And what the probably most important parameter here is you should not forget to measure salinity. As I was mentioning introductory, the salinity can change the freezing point depression. So measuring salinity of a sample, again, should be a standard in ground site investigations in permafrost environments. And when it comes to the frozen soil, you want to look at bulk density, the thaw weakening susceptibility, what is your thaw consolidation, what is the unfrozen water content, depending again on what type of foundation do you have, what is the creep, what is the strength, what is the at-freeze. So there's different parameters that should be measured and evaluated, but again, that depends strongly what type of foundation you need. So we're not going to take unfrozen, undisturbed, frozen samples and do all these tests for every site investigation, for every building foundation. That really depends on what type of load do you have, what type of foundation you need. In terms of the thermal properties, so for example, a high-risk material construction, you need geothermal modeling. And if you need geothermal modeling, then you also want to have a good understanding of your thermal properties. So what is the specific heat, what is the latent heat of fusion of your material, and what is the thermal conductivity of those different layers, so that you can actually develop then a good calibrated model. And finally, when you have bedrock, these are the types of measures and properties you do want to understand for your bedrock, including here the cryogenic texture. So only because you have bedrock doesn't mean you do not have ground ice. So there can be fissures and fractures filled with ground ice. You can have significantly large amount of ground ice even when you think you have bedrock. So you want to understand what is the bedrock and what is its temperature, and do you actually have ground ice available. Again, the guideline provides some drilling in bedrock, so a table appendix C, where you have different types of bedrock drilling in bedrock with some comments. Now, the final section, which to me is the critical section when it comes to transferring your information to your client, is the reporting. And the section 9 provides a clear structure of what should be included, which points should be mentioned in your report. So obviously you do have your scope, you need to discuss the climate condition. If you're in a seismic zone, you want to talk about the seismicity, surficial conditions, and so on. So it does provide a structure of how you actually develop your work and how to communicate that to your client. And you can also see we want to talk about historic land use. Historic land use can cause disturbance to your foundation. So if a building has already been at the site, then your ground thermal regime looks different to a site where no building was there. So understanding what your site's been gone through is also a critical element. And here it also, under section 9.12, without reading every bullet point, it provides you with what is the information that you as a geotechnical consultant should put in, but also what is the client expecting. So that document also helps clients to see what do I expect from my geotechnical consultant in one of those reports. And last but not least, the recommendations. So having done all the site investigations, that should then lead to the recommendations. And as I mentioned earlier on, we're going then into either I do have enough information to actually do a proper design of my building foundation. I do have enough information to say, well, I need to alternate my design, but I can design. Or at this point, you either say, well, this site is not suitable, or maybe you need additional information. So those are the options, and they need to be clearly developed in the geotechnical consultant's report so that the client understands what is needed and where to go in the next step. There's one point I want to mention, and there's the construction aspects and schedules. We have not, haven't about those here, but there's also a table in table 1, there's a section 914 that addresses some of those constraints. So if you have to build your foundation or doing your site investigation, for that matter, in the winter, it's different than if you do it in the summer. So the scheduling, either on the site investigation themselves, but also on the foundation construction, can often be a driver on what type of foundation design you come up with. And we provided a couple of comments with regard to the seasonality, which is so important, in particular in the Arctic region. And one is the climate condition themselves. Working under certain conditions is difficult. Second is the ground. So if you're working in the winter, your active layer is frozen versus working towards the end of the summer, where you actually have unfrozen active layer that gets you down to the permafrost table easily with a backhoe. But not only that, it's also the access to equipment, and mobilizing certain equipment is easier depending where you are at certain times during the year. So if you have access to a winter road, then a certain equipment can be brought in during the winter, but you must be sure that you complete your site investigation as long as the winter road is open to get the equipment out. If you have to rely on barges, that's a different story, or you just rely on the equipment that is available in that particular community. So there's a lot of aspects that also play a role when we talk about site investigation and foundation design in Arctic regions. And that was in essence a brief overview of this guide that we have. And I'm happy to take some questions. And I just want to mention again that the guideline, the documents are available for free to download from the BNQ website. And you find actually the links in the specific sections. Okay, so now lots of questions are coming in, so that's great. So I'll see. So what's the thermal modeling do you recommend for predicting the freeze-thaw behavior of soft soils tailings? Okay, this is a very specific question. Maybe we'll do that a little bit off topic. So I'll talk about. Okay, so there's other aspects. So how do you measure unfrozen water content, for example? So there's different methodologies. You can generate, again, in the lab, you can generate unfrozen water content curve, for example, using TDR measures or using electronuclear methods to measure that. So you can develop your freeze-thaw, so unfrozen volume content curves in the lab. So that is the typical availability. Now there's also what is the best practice to mitigate uplift acting on piles in the active layer. So there's different methodologies. So one is just you're having sufficient deep piles, so and a sufficient strong pile, so that first of all the add freeze strength is sufficient, so that it's not pulling the whole pile out. And secondly is to also have the pile sufficient strong so that the pile is not ripped apart due to the frost jacking. Another option is you can use sleeves. So if you use a sleeve around the pile, then the frost would grab around the sleeve and not on the pile. Okay, I see there's lots of questions coming in, which is great. So how long would you recommend leaving thermistors in place before readings become representative? Well, this is a very good question, and unfortunately there's not a standard answer because it really depends on the methodology, how you drill, how much you disturb the ground. And if you have, let's say, you do have your monitoring, then you can actually try to understand how your temperatures slowly reach that thermal steady state. But often it is a matter of months rather than days. So let's put that into the general perspective. Okay, so what else? Yeah, how long? So will a plain language version of the standard or a portion of it be developed? I probably would have to go back to Standards Council Canada. I do understand there are actually a couple of very nice pamphlets and simplified version of 4 NICE standards. They have been published early this year. I think the one is on thermosiphons and snow load. And since I don't work for Standards Canada, I don't know, but I think that is also planned for some other standards. So I'm not sure if, Elodie, if you have a comment on that from the BNQ side, if you have been tasked to do that, but I don't know, but it's a very good question, a recommendation. How do you communicate to contractors how the south that a permafrost site erosion would be in their best interest to do when they are worried about liability and costs? Yes, it's a good question. So without building codes, I mean, that's why we do have this guideline available, so that we have that document, I guess, available. So to protect either the geotechnical consultant, to give them the guidance that this needs to be done, but also the owner and even to building inspectors that this is a critical part and it needs to address certain things different in the Arctic than in the South. How do you determine the unfrozen? Okay, ice versus the volume of ice in frozen sample. So yes, I mean, when you talk about the volume of ground ice, so first of all, again, it needs experience to understand that. And then if you keep your frozen sample intact and bring it to the lab, there are various methods, and in the matter of time, I can't go into all the details, but to evaluate through densities and melting it and thawing the ice and then understanding the soil particles and specific gravity. There is a option of how you actually get the volume in your frozen sample. And we don't need it, at least for geotechnical site investigation. You're not looking at super detailed volumetric ice contents to the 3rd and 4th decimal place after the comma. I mean, we need percentages, we need ranges, as you know, whether it's 10%, whether it's 20%, whether it's 50%. Okay, more questions coming in. Are the thermistors useful fully grouted? Also, if there's grout, what it makes for permafrost? Okay, again, a very good question. There's all sorts. So first, do you grout the thermistor into the borehole? Typically, we try not to, because that would then allow later to calibrate the thermistor. So it's always a good idea to use a thermistor string, first of all, for the design. So you're using it to understand your conditions, but then also for permafrost and performance monitoring. So once you completed your foundation design, once you completed your building, you can use it to monitor the performance and do, for example, if you have adaptive engineering, you need to adapt to your design. And at that point, if you're talking now 10, 15, 20 years, it's actually very valuable to be able to pull a thermistor string out of the ground and recalibrate it before you lower it. There are drifts. We know certain thermistors show a drift, and therefore the data are no longer reliable. So you think it's warming, but it's actually a drift in the instrument. So at that point, if you're having a hole and you pull in 1 inch or 1.5 inch PVC, you can lower your thermistor string. Want to make sure that it's not filled with water, otherwise it freezes. So you can use antifreeze to put it in there, and then you're good to go. Okay. Yes, I know there's more questions, and I'm happy to respond them. Probably I'll respond them later. But we're at the top of the hour, and I really want to thank everybody that participated. And I understand that the presentation is going to be available online, and also then at some point, a French version will be available online. And BNQ is going to be responsible for putting everything together. So yeah, thanks everybody. We were quite overwhelmed with the response. I never expected that many people that will connect, and that is great. So it's really seems to be an important topic for everybody. So thanks, and I'd like to thank BNQ and also Standards Council. So maybe Lady, if you want to.
And thank you very much, Dr. Aronson. It was very, very interesting.
Okay, so thank you, everybody, and we'll stop recording. Okay, bye, everybody.